All right, hello class. Today we are going to discuss the factors that influence solubility. We're going to explain the effect of pH on a solubility equilibrium involving a basic or acidic ion. And we're going to talk a little bit more about common ions, which we mentioned previously. And we're also going to look at something called a complex ion. This is the third plate posit of 3 on solubility equilibrium. Okay, so the first factor that affects solubility is the common ion effect. So if you try to dissolve your solute in anything other than water, if there is a common ion in that solvent you're trying to dissolve your precipitate in, essentially it will prevent our precipitate from dissolving. So the solubility of a slightly soluble compound is lowered in a solution already containing one or more of the dissolved ions. So I have my first example here, the molar solubility of barium sulfate in a solution of 0.01741 molar sodium sulfate. So that's the key here. We already have some sulfate in our solution that's going to greatly impact how barium sulfate dissolves. Okay. So I need to write my net ionic equation so then I can get my KSP product expression. This is going to mean KSP is equal to the concentration of my barium, and that's times concentration of my sulfate ion. Bear with me, I lost my stylus and I am trying to write with my finger on a tablet, so I'm going to try my best. Okay, so for this problem, we see that our K value, our KSP, is very, very small. In these types of problems, you'll typically see that small KSP is paired with a very large concentration of the other ion in our solvent. So you can see 0.01741 is huge compared to 1.1 times 10 to the negative 10th. So we could compare those things. If we were just doing this in water, we could set our KSP equal to my barium concentration, which is X, and my sulfate concentration, which is X. Really, this is X squared, right? We could turn on our calculator and just say square root of 1.1 times 10 to the negative 10th, and we would find out that our molar solubility is 1.05 times 10 to the negative 5th. Okay, not too bad, but still fairly small, right? Again, this is what it would be if it was in water. I'm going to put that number up here in the corner so we don't forget. 1.0 times 10 to the negative 5th molar, and I'm going to say in H2O. Okay? It's good just to have that number there because it's good to compare and really see if you've done this problem correctly, right? So if we were to do this for this problem where we have all this sulfate in solution, we can set up our expression, our KSP expression, just like we did above. And the trick here is that since we know our concentration of sulfate normally is very, very small, this way outnumbers it. So essentially all of our sulfate is coming from our solvent. So our concentration of barium is going to be multiplied times our 0.01741 molar. This is my sulfate. And this is going to be set equal to our KSP value. So solve for X. Essentially, the concentration of barium, the molar solubility that we're looking for, is going to be equal to my KSP divided by 0.17, oops, I left a 0 out, 0.01741. Okay, so 1.1 e to the negative 10th divided by 0.01741. Oops, there you go. And I get 6.3 times 10 to the negative 9th molar as my solubility. Okay, so this is in the Na2SO4. Sorry for the bad handwriting there. Let's try that again. Okay, so if we look at this concentration, is this bigger or smaller than if we were to dissolve in water? It's smaller. It's way smaller, which confirms our common ion effect. If we dissolve in a solution with a common ion, we're going to have less stuff dissolve. Therefore, our concentration of those ions will be smaller. You can see that the original concentration appears a lot larger. Okay. So let's try one on your own. What concentration of zinc 2 plus in molarity remains in solution after zinc hydroxide has been precipitated from a solution that is 0.108 molar OH minus? Same setup. Go ahead and solve. Okay, so here is the work that I solved out. Now you don't have to do this bottom part down here with the water unless it asks you to, but I always like solving it to make sure I solved correctly. Because when I compare, I know that due to the common ion effect, whatever I'm solving is always going to be smaller compared to what it would be in water, which is the normal way to solve molar solubility. So I can compare 2.57 times 10 to the negative 14th is super, super, super small compared to 4.2 times 10 to the negative 6th. So I did solve correctly. I just plugged in my concentration. I knew that this is way, way larger than whatever was already in that solution. Okay, so that's the main contributing hydroxide source in this problem. Okay. All right. Next factor, pH and solubility. So solubility can be pH dependent. So we have to remember what pH is. pH is basically the power of hydronium. If we're looking at pH, a couple things to remind ourselves. pH is equal to negative log of H plus. We also know that pH and POH equal 14. We also know that we could do 10 to the negative pH, and that's equal to my H plus concentration, or my H3O plus concentration, depending how you want to go about solving it. So the example we have here, we're going to do kind of qualitatively. We have magnesium hydroxide, but it's in an acidic solution. Okay, so whenever I see H and OH, that's a huge key. What's really happening here? What do we get when we have H and OH? This is a neutralization reaction. Okay, so we've got two main equilibria going on here. We've got equilibrium between our acid ions and hydroxide, and we also have my magnesium hydroxide, and it's becoming Mg2 plus and 2OH minus. Okay, so this is my second one. So let's think about this. If I keep adding acid, which way is my first reaction going to shift? To the right. All right. If that shifts to the right, my OH concentration is going to go down. So if my OH concentration goes down, what's going to happen to my concentration of Mg, my MgOH2? It's also going to shift to replace it. So overall, by adding acid, we can decrease our OH. So OH minus decreases. And that causes the equilibrium to shift right. And when it shifts right, we get more of our precipitate or our solute dissolving. Okay, now we could actually calculate exactly how much. We'll do that in our next problem here. Okay. So in this problem it says calculate magnesium 2+ from a saturated magnesium hydroxide solution, magnesium hydroxide in a buffer solution of pH of 12. Okay, so a couple of things we have to remember here. Again, pH of 12, pH is equal to negative log of H plus. We also know that pH and pOH equal 14. And then I could also say pOH 10 to the negative pOH equals my hydroxide concentration. Before on the last slide I showed you 10 to the negative pH is my H plus concentration. Same thing. Or same equation, rather. It's not the same thing. pOH and pH are very different, but it's the same equation. You could do either or. So throw back to some of the acid and base stuff that is coming, and it is coming very soon. Okay, so I know that if my pH is 12, my pH of 12 really means that my pOH is going to be 2. And if my pOH is going to be 2, that really means that my concentration of OH that I'm starting with in this problem is 10 to the negative second. Alright, so if we think about our equilibria that we have here, we have magnesium hydroxide. We're trying to see how this dissolves. We've got our Mg2 plus and our 2 OH minuses. Okay, clear that out so you can see. And then we also know that we've got our competing reaction of H plus and OH minus. Okay. Now, something we need to know for this problem is our KSP. I've gone and looked up our KSP already. KSP for the magnesium hydroxide on the table that I'm using is 8.9 times 10 to the negative 12th. It depends on what table you're using. Okay, but we could set it up almost like a common ion problem. The tricky part was just figuring out the OH concentration. Alright, so we know we've got our magnesium 2 plus, we've got our hydroxide, this is squared, and this is equal to 8.9 times 10 to the negative 12. Okay. Well, we have our hydroxide concentration. We just need to plug that in to get our concentration of Mg. Alright, so just like we did on the last problem we walked through, we've got 8.9 times 10 to the negative 12th, and it's going to be divided by my hydroxide concentration. Well, in this case, hydroxide is 10 to the negative second, and we're squaring that. Okay. So I've got 8.9 e to the negative 12th, and then I've got 1 e to the negative second squared, and I end up getting molar solubility of 8.9 times 10 to the negative 8th. Okay, negative 8th molar. That is my concentration of magnesium 2 plus. Now this is still a very, very small concentration. Essentially, this is already a very basic solution. So in this case, let's analyze it. If this is a very small number for my magnesium 2 plus, that means a lot of this is still solid. If you think about it, pH of 12 is in that basic range, which means we have a lot of OH. 10 to the negative second is a pretty substantial amount of OH minus in terms of the logarithmic pH scale. So if we have a very small amount of magnesium 2 plus, that means we must still have a pretty substantial amount of solute. Not a lot of it dissolves. This is definitely saturated. Okay. All right. My last factor, complex ions. So a complex ion contains a central metal cation surrounded by a number of ligands, which are surrounding ions or molecules. So one of the examples we have here is zinc hydroxide. Zinc hydroxide, when it's in the presence of ammonia, actually forms a complex. So hydroxide is the spectator, so to speak, here. We care about the zinc 2 plus. Zinc 2 plus can actually covalently bond with four NH3 molecules to form our complex here, our complex ion. And we would end up getting zinc, and it would just look like this. NH3 with a 4 on the outside, and then it's our 2 plus charge. Okay, so this is our complex ion. We'll get into naming complex ions a little later down the road. I believe this is called a network covalent, but I have to double check on that. It's been a while since I've looked at those. The key here is that if we have zinc hydroxide, we have to look at two equilibria going on, okay? We know that we've got the equilibria for zinc hydroxide, zinc hydroxide dissolving to give us zinc 2 plus and our two OH minuses, okay? Now, it is usually pretty preferential for some of these complex ions to form. In fact, complex ions are used to drive the reaction in a certain direction so that things dissolve more. So if I have zinc 2 plus being used up, this will essentially go to completion. These typically have very large values, these large K values, these complex ions. So this will essentially shift to completion. If we shift, that means my concentration of zinc in my original equilibria goes down, and we need to now dissolve more to replace that. It's a giant equilibrium game. So it's nice. A lot of times when we're going back to that selective precipitation and that qualitative analysis that we were talking about in the last play posit, although I talked about it very briefly, there's that scheme that we can use to kind of selectively pull out a bunch of different things in solution. Complex ions are great for that because we can dissolve a bunch of things that are solid. We can also push the equilibrium backwards so that we can end up putting things back or pulling things out of solution in that way. And we do that by forming these complex ions. Okay, have a great night.